Hello my dear students and welcome back to the chemical kinetics chapter. So students, in the previous class we have studied about what is meant by molecularity of a reaction and what is the difference between molecularity of a reaction and order of a reaction, and also we have solved some of the numericals based on the order of a reaction. Okay, so in this class, which is a very important class, we are going to study about a concept called as integrated rate equation or integrated rate law. Okay, see, you already know now that rate of a reaction, for example, here I have considered a general reaction wherein A moles of A is giving us a product. Now the rate of this reaction can be expressed in two ways or in two different ways. First one is, see here, the rate of this reaction is expressed in terms of what? The decrease in the concentration of A in a certain interval of time. Okay, so this equation is from this equation you can calculate what is the average rate of a reaction, and you can also calculate what is instantaneous rate to some extent. Not accurate instantaneous rate you will get, but you will get to somewhat a small error will be there, but you will get a instantaneous rate. Now next equation, okay, this also expresses the rate for this reaction. Okay, but here it is expressing how the rate of the reaction changes when the concentration of this reactant is been changing. Okay, from this reaction you cannot calculate instantaneous rate. You can just calculate what is the effect of the concentration of reactant on the rate of reaction. Okay, but this rate equation can help you, or this equation will tell you what is the order of the reaction. Okay, what is the order of reaction? This reaction cannot tell you what is the order of reaction. Okay, this reaction will tell you what is the order of reaction, but this don't tell you about instantaneous rate. Okay, these two rate equations are called as differentiated rate equations. You know the meaning of differentiate or differentiation and integration, you know, in mathematics you have studied it. So these two equations are called as what? Differentiated rate equation. When I say differentiated rate equation, means they will tell you the small portion of the reaction, not the complete portion. What is happening throughout the reaction, that we will not come to know. See, here only you can say from this rate equation we can say what is the rate or what is the change in the rate after certain time or in certain interval of time, what is the change in the concentration. Okay, but this is applicable to what? Small portion. Differentiated means D, some interval of time is required. Within that time interval, what is the change in the concentration of the reactant? In that way we are expressing it. Okay, so differentiated rate equations will tell you about a small portion of the reaction. Now we need to get one equation, okay, which can give you instantaneous rate, and also it can tell you about order of the reaction. So what we will do, we will integrate these differentiated rate equations. What we will do, we will integrate this differentiated rate equations, then we will get one rate equation that is called as integrated rate equation, that is called as integrated rate equation, or it is also called as integrated rate law. See, what is the importance of the integrated rate equation is, the integrated rate equation gives the relationship between concentration of a reactant at different time and rate constant. See, it is covering everything. Rate, from the help of rate constant you can calculate the order of the reaction, and with the help of concentration of reactant at different time intervals you can calculate the instantaneous rate. Okay, for your convenience I have drawn a graph here. How do we calculate the instantaneous rate? Okay, we will plot a graph of what? Concentration versus time. Okay, so this graph is expressed in terms of reactant. So as the time is increasing, the concentration of the reactant is decreasing. Okay, so now to get the instantaneous rate, what we will do, we will draw a tangent. Here you can see we will draw a tangent, and the slope of this tangent will give you the instantaneous rate. Means what is the rate of reaction at this particular time? This is the concentration left. At this time, this is the concentration of the reactant. Okay, this is how we calculate the instantaneous rate. Okay, and whenever you express the rate in terms of reactant, see here you will get in terms of negative value. So slope value will also be in negative, and here slope is OA by OB. Okay, now as we know that what we are doing now, these two differentiated rate equations are not convenient to calculate instantaneous rate and order of the reaction. We will integrate these two rate equations, and we will get one integrated rate equation which will help us in calculating both instantaneous rate and as well as order of the reaction. Okay, but one thing you have to remember, what is that? Integrated rate equations are different for different ordered reaction. What this mean? See, in previous class we already know that there are different ordered reaction. What are those? Zero order reaction is there, first order reaction is there, second order reaction is there, and fractional order reaction is there, and pseudo first order reactions are there. So there are different types of ordered reactions are there. So for each different ordered reaction, the integrated rate equation will be different, and that's what we are going to derive today. Okay, so in your syllabus there are you people actually have got a zero ordered reaction, means integrated rate equation for zero ordered reaction and integrated rate equation for the first ordered reaction. See here in bracket I have written 3 marks or 2 marks. So please students remember this or mark is that in the board examination from this integrated rate equation, okay, definitely there will be a question on 3 marks or 2 marks. Definitely there will be a question for 2 marks or 3 marks, that is derive the integrated rate equation for first order. If it comes, it will be for 3 marks, or if they are asking you derive the integrated rate equation for zero order, it will be for 2 marks. Okay, now let us derive those equations one by one. So students, now we will derive the integrated rate equation for a zero order reaction. Okay, now consider a zero order reaction wherein a reactant A is there and it is giving you products. Now we know that the meaning of zero order reaction. What do you mean by zero order reaction? In zero order reaction, the rate of a reaction does not depend on the concentration of reactants. Okay, so now let us proceed with this. Okay, how do you write the rate equation for this rate? We know there are two differentiated equations, so we can write it as minus dA upon dt. Okay, let us say this is as equation 1. Okay, and another equation is rate is equal to k into a to the power 0. Why 0 here? Because it is a zero ordered reaction. Okay, this simply means what? K. Why simply it will come as k? Because anything to the power 0 is 1. Okay, so let us say this is as, so rate is equal to rate constant for zero ordered reaction. So let us call this equation as equation 2. Okay, now equate equation 1 and 2. So what you will get? Okay, so rate is equal to minus dA upon dt is equal to k. Okay, now I will rearrange the terms. Rearranging the terms. How I am rearranging the terms? See, what I will write simply dA is equal to minus k into dt. Okay, what I have did? So I have taken this dt this side and negative sign on that side. Okay, so then integrate, let us say this is as equation 3. Integrating equation 3 on both the sides, on both sides, what we will get? So integration minus k into dt. Why minus k we are writing outside? Because it is a constant. So we will write outside and we will integrate this. So let us see what we will get after we integrate this. So we will get it as concentration of A is equal to minus kT plus C. Okay, here C is integration constant. Integration constant. Okay, and let's call this as equation number 4. Okay, now how do we find out the value of C? How do we get the value of C? To get value of C, when t is equal to 0, when time is 0, okay, what will be the concentration of A? It will be A naught. When time is equal to 0, let the concentration of A is equal to A naught. This is the, when time is 0, the concentration of A will be A naught, means initial concentration. Put this value in equation 4. Put these value in equation 4. So what you will get? A is equal to minus k. What is the value of t? T is equal to 0 plus, this will be A naught, sorry, A naught. When t is equal to 0, A value will be A naught. So this will be A naught, right? Let us write it properly. A naught, okay, plus C it is. Okay, now this will become 0, so it will become as A naught is equal to C. Okay, equation 5. Put the value of C in equation 4. What we will get? So put that in that. So we will get A is equal to minus KT plus, what is the value of C? It is A naught. Okay, now this we call it as integrated equation for zero order reaction. This we call it as integrated equation. Say equation 6. We call it as integrated rate equation for zero order reaction. Okay, or we can write, how we can write this as, see, KT you bring this side. Okay, this, if you go that side, what will happen? So KT is equal to, or let us simplify it and then write integrated equation properly. Okay, KT you bring this side, so KT is equal to, this will stay here only, so A naught minus A. Okay, this I have rearranged it to get a proper value. Then what will happen? So K is equal to A naught minus A divided by T. Okay, above equation is called integrated rate equation. Is integrated rate equation for zero order. For zero order. So remember, this is equation 7. Equation 7 is called as integrated rate equation for zero order reaction. Now in some textbooks they will prefer a different one. Let us see how they will write that. Okay, say I'll write it here. I'll consider the same reaction. A is giving me product, or let it on this side. A is giving me product. Okay, then I will say that when T is equal to 0, let the concentration of A be A and the product will be 0. At time T, it will become as A minus X, and this will be X. What this mean? At this time, okay, X amount of product is formed, means this much amount is been taken from the reactant, so it will become A minus X and X. Now what I will write is, so A minus, so now here I can write as A naught is equal to A and A is equal to A minus X. Okay, then A naught minus A is equal to this. How can you write? A minus this, so this will become as A minus of minus X. So this will get cancelled, so minus minus into it will become plus. So A naught minus A is equal to X we can write. Okay, then these value only we have to substitute here. So in equation 6 we substitute, what we will get? Or let us say from equation 6 if we start these values, if we start in this, what we will get? See, A means what? A minus X. Put these values in equation 6. So what we will get? So equation 6 means we will get concentration of A minus X is equal to minus K minus KT plus A. Okay, so again rearranging the terms, so what we will get? KT is equal to A minus of X, so we will get it as KT is equal to this A get cancelled, so minus into minus it will become plus. So this we can in short write it as X upon T. So some textbooks prefer this also. Okay, so whichever will become comfortable for you, you have to substitute that value. Means from here only you can start. See, from here only you can start substituting those values. Okay, that I will give it up to you people, that again for the in that way you have to express. Okay, so this is how we derive at the integrated rate equation of zero ordered reaction. Let us see how. Okay, what we have done, we have considered a zero ordered reaction, which is reactant A is there and it is giving us the product. Okay, and we know we can express the rate in two ways, that is rate is equal to minus dA upon dt. Okay, and another one is rate is equal to rate constant into the concentration of A with some power. This power is 0. Why? Because order of the reaction is 0. So this rate is equal to K, means rate constant. Okay, then equating these two equations, what we will get? Okay, this is what we are getting it. Then we are rearranging the terms. Here we are taking this side and negative side on negative sign on this side, so what we will get? dA is equal to minus K into dt. Now this is our simplified differentiated rate equation, we can say. What it is a simplified differentiated equation, but what we are calculating, we are deriving at integrated rate equation. So we have to integrate this differentiated rate equation. So on integration, what we will get on integration? So we will get these values. We will get these values. Okay, here what is C? C is integration constant. You already know, if you have studied integration, then you will get to know why this constant comes. Okay, then how to find the value of C? Okay, to get the value of C, we have to consider when time is 0, from 0 to A. To arrive at A, how much of time, that we have to consider. Okay, so when time is equal to 0, concentration will be A naught. So this only we have to put in there. So we will get what? A naught is equal to minus K into time is 0 here. Here time is 0, so plus C. Okay, then we will get the value of integration constant is C is equal to A naught. Now you have to substitute the value of this integration constant in this equation. So what we will get? This is equal to, that is concentration at time t is equal to what will be this is what we are getting. Again we will rearrange it. Okay, then it will become as KT is equal to A naught minus A. Okay, this I think simple mathematics is there. You must understand what how did I arrive at it. Okay, then what I have done, I have kept the rate constant on the LHS and I have taken T on the RHS. So this is this equation is called as integrated rate equation for zero ordered reaction. Then we have also seen the other form. Okay, I prefer this equation when it comes to competitive examination. Okay, you will better understand it. What is X? X means what? Amount of product formed. You can remember in that way also. X means amount of product is formed. Okay, this is what how we arrived at the integrated rate equation for zero order. And for how many marks they will ask? I have said it will be for 2 marks. Remember this. They will be asking derive the integrated rate equation for the zero ordered reaction. See, as I have said earlier, what integrated rate equation tells us? Integrated rate equation gives the relationship between concentration of the reactant at a different interval of time and rate constant. So from this you can see, here we have got a rate constant, here we have got how much of at a time t how much of reactant is left. So all these three are covered. From rate constant we can calculate what? Order of the reaction, and from this equation we can calculate what? Means at this instant of time what is the amount of reactant left. So instantaneous rate also we will get the order of the reaction also. Okay, now we will see, I think I'll give 2 seconds, or you can pause the video and you can write this derivation. Okay, then moving on, let us see some graphical representations. Based on this, many questions will come in competitive examination. So I'll go to that part now. Okay, I'll go to that part. Let us see. First, let us write the integrated rate equation for zero order reaction. What it is? A is equal to minus KT plus A naught. Okay, this only we have arranged. Now this equation seems to be like Y is equal to mx plus C. Okay, then this has to be plotted on y-axis, and x means time, so time has to be plotted on x-axis. Then let us see how we'll get the graph. So this is what the graph looks like. Okay, what we are plotting? Concentration of A, and on x-axis what we are plotting? Time. Okay, and this is what we are plotting. Okay, here you can see there is a minus symbol. Means what? See, the graph will come like this. Okay, this value or this intercept is what? Your A naught, initial concentration. Okay, when time is 0, here when time is 0, what is the concentration? A naught. So this intercept is representing you initial concentration. So here as the time is increasing, amount of A means what? A minus X. From here you can easily understand. So A means amount of reactant left, X means amount of product formed, A minus X means how much of reactant left. Okay, so as the time is increasing, amount of reactant left will be more or less? It will be less. That's why we will get a graph like this. Okay, then the slope, then slope value will be, slope is equal to minus K. Slope is equal to minus K. Understanding, student? So in the competitive examinations they will ask this. They will give different type of graphs, and they will ask you to identify which of the graph represents you the zero ordered reaction. Then another form also we can say, see, I'll plot another graph here. Here I am plotting rate versus concentration. What I am plotting? I am plotting a graph of rate versus concentration. Now from the definition already you know what is that? What is a zero ordered reaction? A zero ordered reaction, in a zero ordered reaction, rate of the reaction does not depend on what? Concentration. So rate always remains the same. whether the initial concentration from 0 to till here, however the concentration is increasing or decreasing, the rate always remains what? It will remain same. So they may ask you this question also. Okay, any of the graph they may give you and they may ask you the question on this. Okay, same time here, don't forget, in the graphical sometime they may ask you, like here I'll write for your simplicity, like a minus x is equal to, this again will remain as mx plus, this means what, or minus kt, this means a. Okay, so value in the graph what will be, this is the value of a, here I'm writing for your simplification, this means what, a minus x, and this is your time slope is equal to always minus kt. You understanding it? Okay, then next we will go for a first ordered reaction. So students, now let us see how do we get the integrated or how do we derive the integrated rate equation for the first ordered reaction. Consider a first order reaction wherein R is the reactant which is giving me the product. Okay, so we know how to write the differentiated rate equations. So first one, R is equal to minus dr upon dt. Okay, and another one is R is equal to, R means rate itself, so k into R to the power 1. Why power 1 I am writing? Because it is a first ordered reaction. So equating these two equations, okay, so what we will get, rate is equal to minus dr upon dt is equal to k into R we will get. Okay, so we will rearrange it again, rearranging the terms, means R I am taking this side, same terms I am taking on the same side. So what I will get, dr upon R is equal to minus k dt. Okay, so now what we will do, this is again our what, simplified differential equation. Now what we have to do, we have to integrate. Okay, let us integrate. Say this is equation 1 only, here only, as per your convenience you can take. I hope you are understanding it. Integrating equation 1. So what we'll write, R is equal to again minus k into dt. On solving we'll get what, ln of R is equal to minus kt plus c. Again what is c? C is an integration constant. So integration of this equation we will get ln of R. Ln means natural log. Okay, so this we will study in integration. Okay, so I will not go in detail of that. Okay, now let us say this is equation 2. To find the value of C. Okay, in previous that is when we were deriving the integrated rate equation for zero ordered, again there was also an integration constant. How did we get the value of integration constant? Like at time is equal to 0, concentration of R will be initial concentration, that I will write it as R naught. Okay, put these values in equation 2. Put these values in equation 2. What you will get then? Ln of R naught is equal to minus k into 0 plus C. Okay, why 0? Because the time we have taken as 0. Then R is equal to R naught, therefore this will become ln of R naught. So ln of R naught is equal to C. Okay, now substitute this value in equation 2. Substitute the value of C in equation 2. What you will get? See now, ln of R is equal to minus kt plus, what is the value of integration constant we have got here? Is ln of R naught. Okay, This is again we can say the integrated rate equation, but again let us simplify this. So if I can write it as kt is equal to ln of r naught minus ln of r. Okay, then if you are familiar with logarithm and all, you can understand it as ln of r naught divided by r. Okay, this becomes like this. Okay, so again keep the k here only, then what we can write? So therefore k is equal to 1 upon t into ln of r naught divided by r. This you can call it as integrated rate equation for first order. This you can call it as integrated rate equation for first order. But again ln is there, so let us convert it into the log of base 10. So what we can write it as now, k is equal to, now if you convert this natural log into logarithmic to the base of 10, it will become it as 2.303 divided by t log of r naught upon r. Now this equation is called as integrated rate equation for the first order. So which equation is that now? So above equation is the integrated rate equation for first order. Remember, so simple it is. Again, what we have done, we have considered first order reaction in which reactant is giving us a product, then we have expressed the rate for these reactions, then we have equated them, then we have rearranged. In rearrangement, what we have to do, what are the similar terms, take them on one side, like this dr and r is here, so take them on one side. So we have taken it on one side, though this is our simplified simple differential equation. Then we have to do what? We have to integrate. So when we integrate, what we will get? Ln of r is equal to minus kt plus c. Okay, then what is c? Again it is an integration constant. How do we calculate the value of integration constant? That we have to consider the initial concentration, and at initial concentration time will be 0. So when you substitute the value of these in this equation, we will get the value of integration constant. Again substitute the value of this integration constant in equation number 2. So what we will get? Ln of r is equal to minus kt plus ln of r naught. Again this is what? This is also the integrated rate equation for first order. But again we have to simplify further. Okay, then on simplifying we will get it like this. Or kt is equal to ln of r naught upon r. Okay, so again time I have taken on again RHS side. So k is equal to, k means what? Rate constant is equal to 1 upon t into ln of r naught by r. Again so what we have done, we have converted that natural log into logarithm to the base of 10. So this, when we convert, this is the integrated rate equation for the first order. Again in some textbooks they'll prefer in different way. What is that? Again I'll write for you people. See, I'm already telling you that this video may be around 40 minutes, but it is a very important class, don't miss this. Okay, so again at t is equal to 0, this will be initial concentration A and the product will be 0. At time t, this will become A minus x and this will be x. Okay, then r naught, I'll directly writing r naught minus r is equal to what? It will become a minus x, this will become x, isn't it? Okay, then substituting the values, what you will get? Directly I'll go for this equation. Okay, so what I will get in the equation is as k is equal to 2.303 divided by t log of, what do you mean by r naught? R naught value will be A, initial concentration. When t is equal to 0, initial concentration will be there. So it will become as log of A divided by A minus X. both equations you can use, but this equation will be lot useful for us, okay, because from this only we can make our we can understand how did we arrive at this equation. Okay, sometimes some students get confused. I have seen over the years that some students will get confused, what is R naught, what is R, but here when we simplify it like this, initial concentration is A, then X refers to the amount of product formed at time T, then they will understand it, and then especially in numericals this type of solving will help. Okay, so this is what today we have derived what integrated rate equation for the zero ordered reaction and integrated equation for the first ordered reaction. In case of integrated rate equation for zero ordered reaction, we have plotted the graph also. Okay, regarding this, the plot of the graphical representation of integrated rate equation for first order, that I will consider in or that I will take it in the next class. I hope this you people have understood it. Okay, and definitely this is the most number of times asked question in the question paper, that for 3 marks, okay, derive the integrated rate equation for first order reaction. Most of the time from this chapter 3 marks question will be this only. Definitely it will be either, see, for 2 marks if it is coming, definitely it will be either integrated rate equation for zero ordered reaction, or 3 marks then definitely this. Okay, be prepared, practice it. You have to practice. Those who are below average and struggling to pass in the examination, then these are the 2 questions which will definitely come, means 100% you have to do these derivations, because definitely these questions will be asked. Definitely if this integrated rate equation is appearing, then integrated for a zero order will not come. If integrated rate equation for zero order coming, means this will not come. If both are coming, that is a bonus for you. Okay, so in the next class we will see the graphical representation, or what type of questions will come on graphical representation of integrated rate equation for the first order reaction. Okay, thank you students.